Good afternoon, guys. All right, so I was just existing. I was on my way home, and what I saw was a very mediocre stream. No names gonna be called out. However, what I'm trying to do for you guys is better answers. What pisses me off a lot about other physicists is that they typically would care too much about giving you the right answer that they aren't giving you a useful answer. So I'm here today to explain to you guys any question that you'd like to ask and actually give you a meaningful fucking answer. So I have experience in information theory. That's what I am. And what that means is basically I studied the standard model. And what that means, I studied the standard model and how it actually has lots of implications in all facets and domains of your life. So one aspect of physics, and what I have up here today in this green screen, is an explanation. So a lot of classical phenomenon that occurs in the world, one instance is basically electromagnetism. What that one stream that I was watching that has his thing like ask a physicist, whatever the fuck, um, he would say electromagnetic phenomenon is like a perturbation of a quantum field. Okay, of course, but that's not useful for the average person. So what I hope to do is to answer any questions you have regarding, physics or anything of reality, but actually give you useful answers, not give you bullshit mathematical like conjecture. Obviously, the math is useful and that is what we use. But if you're asking a question, you need a translation. And the fact that he's not actively translating for you pisses me off. So please, if you have any questions or any interest in the universe, ask away here, because he would basically give very basic bitch answers. I'm gonna say it. I'm gonna say it like that. I'm gonna start some beef right here. Physicists versus physicist beef. This is what Newton would have wanted. So yeah, like you guys out there in the TikTok universe. Newton, Isaac Newton, you know what he would have said? He's like, "Oh, so you have a global communication network, and what are you guys doing with it? Are you guys discussing? Are you having conjecture arguments? Are you advancing the field at the rate of communication, instant communication? Are you telling each other, no, you're fucking bullshit? Is that what's happening?" No, Newton, we're not, because people are too afraid to speak their mind. So yes, so that's what I'm here for today, to give you guys the no BS, the true answer of whatever you'd like to know about. So far there's been one person that has actually been here this whole time. Uh, Hello. Do you have any questions, or where would you like this domain of discussion to go? So um that's the purpose of this. The purpose of this is to actually help the general population to perform Newton's dream. So as long as we don't have any questions, Newton is rolling in his grave and he's like, "Oh, I invented calculus for some asshole on the internet to basically say, you don't understand linear algebra, so I'm not going to explain anything about the quantum field theory to you." But ugh, it's because and then when you do ask a question, he's like, "Well, it's all actually hidden in the math." I'm like, "Okay, bro, can you not translate it?" I'm like, "It is untranslatable. The quantum mechanics is just quantum mechanics. It is just math." So please, that's what we're here for today. I'm here to live Newton's dream. For now, for now, ask ask questions. Ask questions. That's what this is for. That's what the discussion is. Ask a physicist. So I'm gonna freaking answer some questions while I enjoy some milk. So yeah, we're gonna cool it down now because the anger has been spoken. The anger has been spoken, and the word has been said. What is string theory? Great question. So I'm gonna give you three levels of that answer, not just the asshole answer that string theory is the mathematical approximation for how the universe works. So we have the Cork model, of course. So yes, I'm gonna go through three levels for everything, like advanced, like the bullshit technical. Then I'm gonna go translation. Then I'll go very simple. So my opinion is the last one. So string theory. To answer that real quick, string theory is currently just a mathematical model to try to change everything into harmonics. the reason we want to do harmonics is because it makes the math easier, and it also gives us theoretical experiments to eventually do to test what makes an up quark, what makes a down quark, and basically what it's going to eventually realize, what the hope is with string theory, is that everything is exactly the same, which is energy and vibration. That's the goal of string theory. Now, where is it right now? String theory has 11 dimensions that they work with, and those dimensions are not necessarily concrete. And in my opinion, the direction of string theory right now is kind of horseshit, because they're not using what they're trying to do, the end purpose. They're not using the end goal. The end goal of string theory, like we started with, like I said, is we're trying to use just pure energy and then pure frequency. What are harmonics? Great question. We're going to get to that next. First, I'm going to go for the next question. Okay, quantum immortality. Quantum immortality is the hypothesis that consciousness, because you only ever have the binary state of you are either conscious or you are not conscious. Anytime you have a binary, and this is why my answers are much better than that fucking asshole, Dr. Fucker, I'm going to leave it there. I'm sorry, I can't get too heated. You know, physicists can't clash that much. So, because there's a binary, anytime you have a strict 0 or a 1, anytime you have that, you have quantum properties. It just so happens that in classical mechanics, your quantum properties and your percentages are simple thresholds. But in quantum mechanics, when you have a threshold and you have a what's called probability function or an event occur. So if, and it's basically if statements. So we're gonna answer the question, quantum immortality. So now we have 0 or 1. When you're alive, you are always observing in 1. The theory behind quantum immortality, and the reason why it's not necessarily actual theory, it's more like hypothesis, is that if I am only ever able to see my 1 state, therefore, it doesn't matter if I'm ever dead, because that 0 state will never be observed. Because the 0 state will never be observed, therefore, there's always some probability, some universe in which the observer always lives. Basically, anytime you have a split decision, whether you are alive or you are dead, that opens up the many world interpretation. That's why quantum immortality is hypothesized to be one solution to why you are alive and why you observe that you are alive right now and not dead right now. That's one thing. Do I believe that we live in a simulation? No, because the standard model shows us that everything is infinitely recursive. Theoretically, it could be coded. The entire universe could be coded. But because everything is recursively coded, it is impossible for one place to be the root. And based on how the particles are both infinitely up and infinitely down, in terms of information that they can store, it is impossible. There is no end. The universe is fundamentally infinite by its own informational creation. I can go more into that, and that's a good question. It's a good topic to discuss if you guys would like to know more about it. What are harmonics? Harmonics are resonance phenomenon. So when you have an event and you are doing it for the first time, that is the largest it could possibly be. You have all of your energy invested in that first event. And now I'm not just giving you harmonics in the basic bitch answer like that fucker would do. I'm not going to do that. I'm going to give you the useful answer. Harmonics existed everything in your life. I study information theory. Information theory is how information, including events in your real daily world, like right now, this is a harmonic. User, if this is your first time observing me and a conversation with me, that is your first harmonic. You're going to get the most conversation or the most utility out of your first event. Now, don't overvalue your first harmonic, because now there's the second harmonic. The second harmonic is where you have two events, two phenomena. And in terms of actual actual phenomenon, so it changes when you go from events, which is quantum, that's quantized information. When you go from events, when you go to phenomenon, it's weird. I have this all constructed in my head. I understand this stuff because I study it. I study these conversions. Whenever we are discussing quantum, you're discussing events, thresholds, triggers, 0, 1, and the dualities in between. Whenever you go to the analog world, that's classical mechanics. That is where analytical mechanics comes in. You're no longer doing quantum mechanics, which is linear algebra. You're not doing linear algebra for the purposes of probability and combination. You're doing linear algebra in the classical side for the purposes of location and position. So it gets pretty interesting. Any more questions? Because you guys actually have good questions and an actual person to answer these questions in a legit way. So I appreciate the fact that there's at least 5 people here. That is certainly useful. However, I wish this audience could be the 200 that doctor guy has, because you guys deserve the real answers and actual useful information, not just some pretentious asshole that would basically say the answer lies in the math. Well, can you translate the math, brother? No, you can't translate the math, brother. Then you're freaking useless. You're not. You're just a what I would call a calculational slave. You are gonna do the math that we will describe for you. What do you think about the Big Bang? There's nothing wrong with it. I think it is a great model for reality. The Big Bang actually has more utility than he would describe. So he would say the Big Bang. Oh well, the Big Bang. It's just the event in astrophysics. It's the beginning of the universe. It's some far distant point. All it is, the theory of the big. He would give you the basics information. He could basically describe the wiki page. He wouldn't give his opinion. He wouldn't give you actual useful information of it. I'm going to expand that question. You know the wiki page. You can look up the wiki page of the Big Bang for what it is. No one gives a fuck about what it is. I'm going to give you the truth. Who cares about what it is? What do you think about it? So, good question. The Big Bang has more than just what it is. It's not just the beginning of the universe. It's also and this is why information theory is the most powerful tool of physics that I'm trying to teach on my channel. Information theory goes beyond just what it is. The question is, why and how can I use it? So the Big Bang exists. So that is, once again, an event. We use the event of the Big Bang and we look to it. We look at what it tells us in terms of information and in terms of like what physics has occurred due to it. We see flow of information away from a source point. We see decay rates and things that form. Complexity arise from distance, from what's called energy mixing. And it's actual energy, because everything began from the Big Bang as high vibrational molecules. If we go to string theory, we'll say these are very high frequency strings that eventually coagulated together to form mass and matter. So the Big Bang isn't just the beginning of the universe, and what really happened. It's not just the beginning of the universe. There's more utility to it. It's recursive. Everything in our universe is recursive. One event does not just end there. The Big Bang isn't just the Big Bang and we talk about it and we're like, damn, bro, science is cool. Don't you want to learn about space? I don't give a fuck about space. I really don't, because space by itself isn't useful. What is useful is realizing that the distances we see in space are physical representations of information. And I've seen this before in terms of like, okay, I want to share with you this beautiful example of what I'm talking about. So, the sun, and it's gonna sound interesting, but this is how you do actual useful introspection. Sorry, man, I'm coughing, man. I gotta drink my milk. What do you know about fluid mechanics? What would you like to know about fluid mechanics? Fluid mechanics is just electrodynamics. Don't ever forget that everything is just... Okay, I'm going to break this down. I love this breakdown of explanation because asshole physicists will tell you there's 4 forces to the universe. I'm going to tell you what's actually useful. If you tell someone there's four forces of the universe, they're going to imagine like wind is different. Like, okay, here's why this is a really good point. Okay, if you tell someone there's four forces of the universe, they're going to assume that wind, for example, because this is a common one, wind is not electromagnetic. Thermal or heat is not electromagnetic. There's no way that heat is electricity. It is. There's no way that wind is just electricity, is only governed by electricity. There's no way, right? It is. You say, and then assholes will say, or basic bitches will say, heat is or wind is caused by heat. Okay, asshole. Go back to the fundamentals. What is heat caused by? What causes heat to occur? Oh, that's the excitation of molecules, their vibration. How did they get excited, asshole? They got excited because photons or vibrations or now I'm going to give you more technical stuff. Excitations from the outside moved it. That's what heat is. Everything is only electromagnetism in your daily world. There are four forces. Gravity, that doesn't really affect anything around you. It's not a regular force in terms of things that have direct utility to your life. So gravity you can ignore because you know how it works. Pretty simple. There's the strong force and there's the weak force. The strong force only holds atoms together. It holds particles together. Is that useful for your life? Does it change how anything around you works? No, it doesn't. Obviously, we have protons and atoms together, but it doesn't explain why molecules come together. It's not that reason. The reason molecules come together is by electromagnetism. So strong force is not needed. Weak force is not needed for your daily life. Everything that you live with that changes your life is electromagnetic. It can be explained by charged particles be moving around other charged particles. Doesn't that blow your fucking mind? Everything you could possibly imagine in your life that exists is electromagnetic. So, just for an example, so you can see, so you can really appreciate another factor of that. Friction is electromagnetic. Whether you can get two things to come apart. Glue is electromagnetic. The thing that holds our stickers to our food items. The thing that lets sugar stick to chocolate or brownies, electromagnetic, static electricity. The thing that lets you taste, the bouncing of the sugar on your tongue, electromagnetic. Everything is electromagnetic, and that fills me with such great passion. Is time travel possible? That is a interesting question. Information can be passed through time, theoretically, but that has yet to be discovered or yet to be engineered in a practical way. Specifically, Reynolds' transport theorem in regards to conservation of momentum. Unfortunately, I don't know the exact theorem. However, what I was trying to explain to you, or trying to show you the direction of look at everything in terms of electromagnetism. This is useful. So this explains domains. The what I have up here, domains. And get into domains and how that may be useful for your question. I haven't had sweets in such a long time. So, okay. What are you trying to ask about in terms of fluid mechanics specifically? So, this is how you guys approximate things. You would use a domain. So what that means, you would pick a specific area. But I don't think the general public really wants to know about how calculations are done. If you'd like to, we can talk about calculational methods. But, what do you guys think so far? Do you guys like this? I actually have 8 people here. Does pineapple go on pizza? Hell no. The taste does not combine. I will say pineapple does not go on pizza, and I will argue with my 4 forces example. Out of all the forces that exist, electromagnetism, the only one that makes everything happen. And I don't think pineapple should go Freaking pizza. Sorry for the coffee, man. I'm so sorry. When it comes to mech E, gravity is very important. We barely talk about electromagnetism. Okay. You got me. You're right. Okay. When you're doing like stability calculations or things that actually have to do with the real world, you're dealing with potentials. One of the easiest potentials to work with is the gravitational potential. Because you're not using the relativistic potential, are you? You're not. Can electromagnetism account for the other three forces? It can account for. Here's the thing about that. Gravity is just electromagnetism exactly the same way. We learn about it exactly the same way. But gravity is what we call absolute charge. So there's no such thing as inverse charge for gravity. That's what that one guy wouldn't have said. I really don't like his explanations. He sucks. Nah, we're working with Newtonian mechanics. Yeah, Newtonian mechanics. But what I was trying to say is that you're not accounting for as height increases, the acceleration due to gravity changes. You guys are obviously using just 9.81. You guys aren't accounting for that small increase in radius because it's not necessary. So yeah, gravitational potentials are very easy for calculations. So yeah, so I'm not gonna answer that. All right, sorry for the coughing. Now do you think we'll have a theory of everything in our lifetime? I do. I do think we will have a theory of everything, and I think I have the fucking solution. I'm gonna say that with balls and vindication. Yes, the solution is the revision to the standard model, is the realization that everything is recursive. It's the realization that you only need the weak force and the electromagnetic force, and gravity only because it's like what's called macroscopic effects. So gravity is its own thing. The reason we don't mess with it is because it has absolute charge. Though, interestingly enough, though, and this is what's actually beautiful about theories of of relativity. You actually need to calculate gravity like magnetism, but it gets complicated when you deal with that math. The reason you deal with gravity like magnetism is because it's absolute charge. So every particle affects every other particle. And particle just means an object that we're using to just locate a mass in space. That's what particle really is. So, I don't know. I don't like going too depth into explanations because, I don't know, they draw away people. So, what questions would you like in addition to that? Yeah, it's because even at that height that planes fly, gravity doesn't really change. Exactly. So, yeah, doesn't really matter. Would the non-binary nature of gravity change if we discover a graviton? Now that is an interesting question. Now the thing is, I think it's very unlikely for there to be a graviton because it seems like energy itself or anything that occupies any amount of oscillation in space, that simple fact that it exists disturbs space itself, which makes sense in terms of and I'm going to go back to complicated for a little bit. In terms of excited fields, I really hate giving the math answer because I feel like it's unintuitive to the average person. They're like, oh, he's describing fields and he's so pretentious, he's up his ass. I'm not trying to do that. So because everything is just excitation, is movement, is a vibration. I'm going to simplify it. It's just a stored energy due to that oscillation. And it inherently is that. The only way for anything to travel through space by itself is, as far as we know, because this is how reality works, is if it's a self-induced oscillation. So if I move the electric field up, I induce a magnetic field. So the reason why photons are free traveling particles is because they induce their own necessary components for their own existence. But it does cost energy to travel through the universe. That is what really causes redshifting to an additional degree. So, so interesting question. Yeah, good point. Well, wouldn't gravitational lensing count as an excited field? Yes, it does. And that's exactly why, as a particle or as light can travel with the curve, it blue shifts. And it's weird. And I know it's weird. It doesn't sound like that's the case, but it is. If light travels with the gravitational field, it blue shifts. And that kind of violates what traditional discussions of what photons do in fields are. The reason why it doesn't violate anything, because the space itself, as you go into curvature, your apparent motion on the flat 2D plane of reality, on the visible plane of reality, like contracts. As you go into curvature, it looks like each unit meter distance you travel is contracted. That is what general relativity really is. I'm not going to tell you any BS like, you see, general relativity is the calculation of no. There are actually 4 spatial dimensions. I'm contrarian to other physicists. They say there's only 3, and the 4th is time. Fuck no. There's 5 by their standards. 4 spatial dimensions, 1 of time. That's how reality actually works. But time isn't even a real dimension. And that's the weird thing. Time isn't a real dimension. Time is simply the difference between 2 motions, 2 points in space. And what's cooler is that and here's the thing that pisses me off. Physicists don't tell you when they tell you that time is a dimension. It's not. Because every time we do a time calculation, we actually convert it into distances of x. And when you go to quantum mechanics, the reason I say that is because things can only move fundamental distances of x, of delta x and delta p. Because we can only move fundamental distances of delta x, you actually have, when you do your retarded potential, when you do your retarded time, so that's why that doctor guy, I won't say the rest of his username, that's the oh shit, this seems sus. Do you have any credentials in physics? Yeah, I have a bachelor's degree in physics. I'm going to get my graduate education later. So I'm glad you're here. You're exactly who I was hoping to discuss. So, what questions or how may I... Okay, I'm not going to bullshit you. Okay, I'm sorry for the ego. Real human being right now. What I'm trying to discuss with you specifically, so the goal of Newton was a discussion. Yeah, but like time is real. No, okay, time is real. But okay, now we're having a physicist discussion. Okay, so what you do with your math, beautiful. I love your geometry theory. And so how everything works, so you guys convert spatial or movement through space, you guys set that equal to time. That's perfect. That's beautiful. Oh damn. Yes, please. Yes, I would love. Okay. Yes, I apologize. For anything. Okay.
Hey,
so
sorry. I'm in the kitchen.
Hello.
I was just scrolling by and I saw like, but time isn't real, and I'm like, wait a minute, what? Let's talk about it.
Okay. So far what I've observed in terms of time is that and this is why I think I thought that's what you guys are working on, honestly. So
Sorry?
What happens is I thought that's what your math does. Because I've seen professors basically explain how you can set distance as time, basically. When we were learning retarded time or retarded time in electrodynamics, you can actually set distances as equal. So that's why I thought when you were talking about your curvatures and the things that are necessary in order to make a quantum field theory, like for quantum electrodynamics, like I thought what you were doing was counting
okay.
all the
forces. So the whole thing that there's a few separate things. One is that we often do this thing where we we solve the problem spatially rather than temporally because it's easier. Also, You're frozen. I don't know if that's me or you. But the other thing is that if things travel, like if some something propagates at the speed of light, like electromagnetic disturbances do, you can use that relationship to associate a duration with a distance. But it doesn't mean that the duration is the distance. It just means that it takes, or that over that duration, the distance propagates that much. Does that make sense?
Yeah, yeah.
Your video froze. I don't know if that was intentional.
No, no. It probably might be my Wi-Fi. I don't know.
Could be either or.
Yeah,
Anyway, I just wanted to pop in. Not, I don't mean to interrupt, but I just heard something. I'm like, what? You know what I mean?
yeah. So that's pretty much what I was trying to say. Okay, okay. One last thing I wanted to introduce. So, what do you think about? Okay, so because everything can be equated to distances, and I personally don't like that is time. I think there's less utility to that. Obviously, it's useful for special relativity calculations, but I don't think that's
Yeah.
necessarily what's happening. I think there is a fourth spatial dimension, and that's why.
Well, but there. I mean, it's clearly evident that. So you and I both agree that we can describe a location in space time, whatever that may be, with four numbers, right?
Yes, the four vector
Whatever.
units.
Yeah, yeah. So, but the thing is that one of those dimensions is qualitatively different from all of the others because you can only go in one direction in it. Like that's the best evidence I have for time being distinct from space. Because in space, like you can travel left and right. You can't go backwards in time, at least not in any obvious way, in the same way that we can move left and right.
True, true. But I feel like that's kind of it feels like a cheat answer. I feel like we're not giving the full explanation to people though. Okay, I agree. I agree. Because the reason why I say that is because it's almost like it only comes out of the math just because obviously as we progress a number upwards, that's what time is. But
What do
it
you
can
mean?
also be it could also be done with just spatial coordinates.
What do you mean
And
when you progress a number upwards? That's what time is.
that so like we said, time is something that can only go forward. So that's one aspect of it. So when we're
Yep.
plotting something, we could do its spatial distance, and we can set that into the thing about relativity. And what I was trying to say is that if we have equal motion, if I have 1 unit x and I do travel that 1 unit x in per 1 unit time, then that's one. When relativity occurs, if I physically travel 1 unit x, but I get an output of half a unit x, then that's an actual curvature. I'm traveling through curvature that causes that.
Or you could just be traveling at a slower speed, no?
What I'm trying to say is I'm physically traveling at 1 unit x. Like my engine would
One
feel like I am
unit,
traveling 1 unit x. But
when you say at 1 unit x, do you mean like a speed, or are you saying like 1 unit? Like, I just think I'm not understanding actually.
okay, so I think when objects approach, sorry about my cough. I think when objects approach
No, you're good.
a curvature through space, and I've noticed this with calculations of it. Uh, if you so we have the flat x plane. That's what we perceive in our universe. That's like the 3D one. If I travel 1 meter on this flat plane, like that in flat space time, I get 1 meter traveled in distance that we can see. If you approach a black hole and I travel 1 meter near a black hole, I physically I did travel. I felt like okay, and you have to explain with a walk. If I walk 1 meter, it's not going to look like 1 meter to the outside observer.
Yeah, that's that's fine.
Yeah, so that's why
But I mean, that's just because distance is relative, just like time is relative. All of these things are relative.
yes, but I feel like the interesting thing is that we're sort of we're equating distance to flat space-time distance.
Well, no, there's just a different way of. So you said you had a bachelor's in physics, yeah?
Yeah,
Did you ever take general relativity?
yes, I did. It
Okay,
was one of the hardest classes.
yeah, no, it like honestly, general. It was my favorite class, but it was very hard. Um, so like it when we talk about distances, the distances that you measure are the distances. It's it's the integral of of arc length, right? That you like right down in general relativity. That's how we define distance. And so the way that the only reason why it appears like it's a different distance depending on what inertial frame you're in is just because basically the uh, the the way that we measure things far away changes, right? Like the speed of the speed of light near a black hole is different from the speed of light outside a black hole, even though it's, you know, 300,000 kilometers per second in any reference frame. Like
Okay.
it's the way that we measure things that make it look different. It's not necessarily that it is different.
I feel like what's happening here is that it's like you have all the advanced knowledge, but I feel like that's what's kind of getting us caught up as physicists. So what happened there is no one's asking why is the speed of light slower. What is the
Well,
physical
we
mechanical
know it
reason?
slows, and we know it well. It slows depending on the direction. It's just because space time is flowing, or rather, space time is contracting. Do you think?
Because
I mean, if you think of like a grid, the grids get the the speed of light will travel the same speed in any across. Light will travel the same number of grid squares, say,
yeah,
in any reference frame, but the grid squares will get smaller or bigger depending on the presence of mass.
I'm saying that the grid squares that okay, yes, the grid squares that light is traveling is always the same. So that's what I meant by 1 unit of thing.
I see.
So
Okay, yeah, I misunderstood.
so as because we're in a black hole, that it's basically just storing more grid squares. So as light is trying to leave, it's still traveling, but it looks
Yeah,
like on compared to flat space time, like it's slowed down. You get
yeah,
me?
yeah, precisely. But I mean that's expected. That's kind of like what we expect to see, right?
Yeah,
Considering general relativity, like that's the outcome. Anyway, I'm gonna drink some coffee. I'll leave you to it. Sorry for crashing your live. Keep
man, that
doing
was
good
beautiful.
stuff,
That
man.
was beautiful.
And go to
Newton
grad
thing
school.
is
It's
incredible.
like if I like grad. I don't know if you planned on it, but like grad school was like the best time of my life. Like I loved it so much. So highly recommend it. Would do it again. Anyway, good luck.
Absolutely. Thank you. So pretty much. So yeah, that's the thing, man. That unfortunately, we have lots of like minor like there's things that are lost in translation. We understand the math as physicists. We understand what's going on, but I feel like sometimes when it's explained to the outside public, a lot of information is lost. So let me see if there's any questions or anything specifically. Where is time in this equation? What specifically are you asking for? Is teleportation ever going to become a reality? I don't know why are you guys saying no to that. Teleportation is possible to become in reality. And actually, that's the purpose of doing what's it called? Uh, what is it called? The quantum stuff at a distance. So when you share two quantum states at a distance, that's the eventual goal that we can transmit the perfect information for reconstruction. Because we can reconstruct atoms, obviously. You can put two atoms together and make so simple example, break hydrogen and oxygen apart, put it together, it's water again. That's okay. We're not trying to teleport water. What we're really trying to do is we're trying to teleport all the information so that when we reconstruct the object, it is exactly the same object um, to prevent destroying it and like damaging the system. So theoretically, the eventual goal will just be to teleport like metallic objects. Those might be the very first objects we can teleport, metallic objects, because you can ionize them, turn them into a gas. You can physically transport the gas, but at that point, you're kind of just doing forging. You're just doing forging at an expensive way. So that's why all this information stuff that we're trying to figure out in terms of like experiments is difficult, but that's the future. That's what we're trying to do. so so teleportation will be possible, but right now it's impractical. Any questions? Damn. I apologize for being disrespectful to that man. Well, just a little bit, just a little bit. Newton still would have been mad just based off the discussions. Unfortunately, I really do agree that Newton would have wanted us to at least be discussing. I love this space. Thanks for sharing. Absolutely. I'm probably going to call it in 3 minutes if there's no questions or anything further. So I'm really glad that there's been more people. Destroying and reconstructing humans sounds scary. That's the super far future. Theoretically, if we do get what's it called, the quantum phase problem, like what's it called? For some reason, I lost it. I lost the memory of what it is. But it's what they're calling. Fuck, what's the problem? I forgot. No, I joined at the end. No, it's okay. Ask anything you'd like, and it could be just extended. One reason I'm going to end it so soon is because it doesn't feel like, there's anything I need left to go. Entanglement. Yes. Thank you. Yes. If we can master entanglement, which really what it is mastering noise reduction. If we can master noise reduction while also destroying, as so to speak, while also deconstructing is what it is. If we can deconstruct atoms carefully, piece by piece. I only found you because of Blitz. I'm so glad you had a chat with him. Very much. What's the discussion? The discussion is any question in physics and anything you'd like to know and anything about reality, pretty much. Because I felt like some of his answers were not satisfying enough or were not introspective enough. It felt like he left them too much at what is correct and not enough about what is or adequate translations about the public. What do you think about quantum computers? They are not what most people think they are. Quantum computers are, and this is what I understand about them. And I think it's so funny is that people are like, what do you know about quantum computers? You've never worked on them. Now the thing about that is quantum computers are literally just the standard model, which is very fascinating. It's like what the fuck? What that means is we're changing how we consider information to exist. So in one essence, quantum computers are just bit calculators, but bits that are allowed themselves to interact with other bits to do calculations for you. So imagine and this is what's cool about it. It's what computer scientists have wanted to done forever. If I push a one, if I send a one into another transistor, that's this one that I send will interact with that one and will output a chain reaction. But the chain reaction is controlled. The chain reaction is basically a function. So it's fascinating because quantum computers are basically they're pre-calculated results. That's how, oh man, I'm both tired as well as a little bit. I feel like you guys aren't following because there's no questions. That's what sucks about it, man. Because like I need discussion. I need discussion to really answer every particular that you may have. Because otherwise, it's a presentation, and a presentation is harder to do off the top of the head. If you look, I've explained it before, but basically the standard model says, and this okay, I'll explain it this way. So, and it's weird because I have to give you a lot of background, but this background is as simple as it can be. So, in a proton, which is an up, up, down. So, an up, up, down is a very stable state. What that means is that if I break my proton state, and this is why I explained it for combat. So, a combat stance is a proton state. This is useful. This is useful. But what's interesting about it is that isn't necessarily quantum computing. What is quantum computing is if you're going to ask the question of a decay state, of a decay reaction. And it's hard to give you an example of how to use it. Quantum computers are currently used for iteration or matrices. That's what they're currently best used for. Where it's a simple repetitive reaction, but you don't want to actually do the actual transistor calculation. You just want to do it can be physically done if you could send a signal that can bounce around and give you an output. Where does that occur? Interference patterns. So quantum computers should really be called interference computers because that's what they are right now. They are not true quantum computers. They are only able to do matrix array calculations. So that's why when you heard about like a computer doing a calculation that that would take humans 10 to the 30. Yeah, but that's only for a M by M matrix that's done to like 1,000 times. Who cares about an M by M matrix that's done to 1,000 times? That might be useful for very niche applications, but that's not useful for what they're talking about. Like, oh no, quantum computers are gonna break prime numbers and they're gonna solve prime number like factorizations super fast. No, not yet. Unfortunately, they will not be unless someone can code an efficient matrix calculation for that. So that's why the real utility of quantum computers is if you can figure out some sort of cascade pattern that pre-calculates what you want to happen, and you can that's really what it is. So quantum computers are limited one by their width. What we mean by width is how wide the cascade can go. Because if you have a cascade, and the reason why you want to be efficient with your bits, because you don't get that many, at least for now. So like it's hard to explain because you have to have a lot of background and structure. But it what I'm trying to say is it's just the standard model. It's basically the standard model and how things interact together. So if you I've showed it on my channel before, but if you have like I'll give you a common particle that decays really well. The kaon, if you have a U and an anti-S, that can decay into other reactions. So what's really happening is we you would send a kaon. You would basically write a function that has properties of a kaon or a particle. It would break apart in its calculation, and whichever part of the function you wanted to have the calculation to check. So like uh, so whatever part of the calculation that matters to you, you can only pick one. So that's why quantum computers are limited for now. You cannot pick all three. You can only pick one because then that cascade continues on the other one. You could pick the other ones right now, but it would break the interference pattern. So you can't. So yeah, relativistic relative perception of time between two entangled particles over a long galactic distance. Okay, allegedly that has occurred, and I wanted to go over an article where that happened. So, and that's the thing that I found really confusing because I didn't like the article's interpretation. So I got to look at the actual research paper. So allegedly, between two quasars of different distances, they said that there's entanglement over light year distances, and that is strange because one that has multiple questions. The multiple question of what it could mean. One, it could mean maybe quasars oscillate at exactly the same time, regardless of where they are in the universe. That would be fascinating if that was the case. That would mean that reality or supermassive, super dense objects are oscillating at the maximum limit of reality. And better than that is at the maximum limit of reality, they can only oscillate at the exact same allowed time intervals. So if two quasars that are different angles in the night sky oscillate at exactly the same phase, such that they cause interference patterns on a polarized filter, this has huge implications. So I really don't like how the article is basically saying like the Bell's inequality has been proven. I'm like, that is the least profound aspect of that experiment that I just saw an article. I was like, what the fuck? There's more to that, and I want to look at the actual research paper. Like, no, what did you guys actually do? You can't just tell me you guys looked at the light of two quasars at a very distance, and you just pass it through an interferometer, and you just look at it, you're like, oh, there's an interference pattern. Whoa, that's cool. It's like, why? The question is why? That's what's way better than that. So all these astrophysicists that are like talking about like, look at the James Webb, look at the galaxies, look at the stuff. Like, what pisses me off is like everybody is on the wrong track. Everybody's like looking at the wrong things, talking about the most dumb, inane stuff. Like, uh, astrophysicists, their actual job description is to prove and check like physics, the maximum possible like limits of physics. The reason why astrophysicists have to learn the standard model and why they hate it is because they don't want to actually learn the standard model. They don't. They don't want. They don't care about particle physics. but it actually matters for their field because everything in the universe is super light. So because everything is super light, you need to understand how these very light molecules and very light particles are actually reacting. So that's why they learn about chemistry and they're like, man, I don't want to do that. I just want to look at stars. Be like, okay, okay, I get you. But they're lost on the wrong things. Like their techniques are all about light and light analysis, spectrum analysis. That's good. It's a good skill. It's useful, but that's not the kind of questions that we could be asking. That's basically it. That's my problem with those people. Can you explain about the time crystal Google made? Basically, allegedly, what happens is that it just allows sorry information to go back and forth without any energy loss. Is it useful? Honestly, it's not that useful. Do you think that James Webb's found aliens yet? I think so. Honestly, I think even the Hubble fucking found some aliens. Honestly, the reality is they're probably just like, nah, I don't want to like, don't post that data. Don't post about that object that's traveling through the sky. Like, just say it's an asteroid or something, and it's X distance from the sun. And the reason why I say it's X distance from the sun because they're trying to account for it in terms of natural phenomenon, but in reality, it's like, why is there a shiny object with this libido or luminati, whatever the fuck it is, like luminosity? But I know they call it libido or something like that. Just in terms of lumens, why is there an object with these lumens traveling at these speeds at this trajectory? And like they basically say, oh, it's one of those distant Oort cloud objects. Yeah, it could be, but another thing about that is that they don't have that luminosity. They don't. So sometimes there's basically anomalies that happen in the sky, and they're like, must be asteroids. Yes and no. You can't necessarily have that luminosity all the time, you know. And then they'll say like, oh, it must be a very shiny metal asteroid. You're like, okay, cool. Since when? How come to those? You know, man, I feel like such a dirtbag for coughing. So sorry. Thought is what holds all this together. We project out our eyes and see our own creation. Is just God experiencing itself in human form. What am I? Close. You're very close. Information theory itself, everything that exists around us is just a standard model, including your thoughts. So yes, you're right. Anything that can be binary, that can be explained in terms of bit information, has already been explained in the standard model, has already existed in terms of particles, in terms of states of particles. So we have already existed before in just random motion of regular particle, like subatomic particles, smaller than quarks. Everything we've ever said, all the bit information of Shakespeare has already been written or encoded, but it's not encoded in our language. It's not encoded in our computers, in how we write bits. It's encoded in quantum bits, qubits, quantum computing. That's how everything is actually encoded in what's called cascade reactions. So that's why quantum computing will actually open up humanity to thinking in an exponential way, because it works with exponential functions. You're not supposed to think linearly. If you think linearly, you're wasting calculation. You're wasting time. You're doing too many small chain reactions when you should be thinking about writing a big chain reaction. That's the purpose of CERN. That is what we're actually collecting the data for. That is what it's actually being used for. So explain Lagrangian mechanics. Lagrangian mechanics are it's basically saying that as you store energy, so basically all the logic of Lagrangian mechanics says is that if I am moving through space, then obviously I have to eventually stop. And if I don't stop, then I have my solid kinetic energy. If there's anything outside that can slow me down or change my kinetic energy, that is potential. That is changing my energy. So Lagrangian mechanics is really thinking about how to view energy conversion. And Lagrangian mechanics boxes a system. That's why we say the Lagrangian is equal to zero. And when it's equal to zero, you have the complete motion of the system fully calculated. When you set the Lagrangian equal to the Hamiltonian, which is the total energy of the system, you get the motion or the transfer of energy. And the reason why the Hamiltonian is better than the Lagrangian, because Lagrangian is only for motion. The Hamiltonian can account for energy loss from decay, from friction. That's why the Hamiltonian actually has more utility in terms of calculation. So, good question. Government got him. Never mind, he was just coughing. Yeah, exactly, man. Everything is energy and frequency. Man, I feel so bad for coughing. Um, Thought created this whole thing, continues to create all we see. Um, Technically, it's thoughts, but it's just a standard model. Everything is the standard model. Explain Mach-Zehnder experiment. Damn, the Mach-Zehnder experiment. Okay. Oh man, we learned a little bit about that experiment in our quantum physics class. I don't remember it off the top of my head, so I can't give you a good proper explanation. But honestly, that should be a video topic because that experiment alone has lots of actual utility in terms of what I'm trying to describe for the benefits of quantum mechanics and what you should actually understand about it. So Mach-Zehnder experiment, yes, yes, I will make a video of that. Explain neutrino oscillations. Good question. Neutrino oscillations, the reason they occur, and that's the weird thing. So neutrino oscillations, one, occur because, okay, I'm not going to say why, not yet. So what happens is you have a neutrino that's, say, a tau neutrino, the heaviest neutrino possible. It's going to flip eventually into a muon neutrino or an electron neutrino. Neutrino oscillations, in my opinion, I think what's happening is like, well, you have mass, but it's like they're very neutral particles. So their mass is kind of like it's a Hamiltonian. So instead of like storing energy in terms of motion, you flip. It's the cool thing is every particle is a two-state system. As far as I have seen, every particle is a two-state system. The only time there are free particles is if you're doing calculations with free electrons and calculations with free neutrinos. That's the only time. But in reality, neutrinos are owed energy as well, but they're very close to being neutral. And electrons are owed energies of the up and down quarks. I made a video in my revision to the standard model. It's like I think it's like part 4 or something where I show you the list. But basically, when I was doing calculations, not calculations, Feynman diagrams for my physics class, I realized there's more to this. Like there's rules to this. Like, oh yes, there is. And the rules are hypercharge and some other bullshit. Hypercharge, the dumbest idea physicists have ever made, honestly. It's like, well, numbers are conserved. Be like, so there's a conservation law here. They're like, yeah, but it's the conservation of lepton law. Be like, so you're telling me we have the most powerful tool in our entire arsenal, the conservation of momentum, which works for particles, and the conservation of energy, which works for particles. But you're not going to use that when you're trying to explain like the change of up and down quarks. No, it's lepton number, or it's like it's hypercharge. Be like, ugh, we got so close just for everyone to dumb themselves down. Um, yeah. Do you think alien life will be similar to human life, or will be looking for a different definition of life? Now, the thing is, alien life would look similar to human life in terms of society, but I don't think we'll ever be able to see actual aliens life like that are like light years away. I think the real solution to the Fermi paradox or like aliens paradox and stuff like that is that they eventually learn to communicate faster than the speed of light. They learn to eventually communicate with quantum oscillations, with noise itself, noise of the universe. That's what I think eventually we learn to communicate with. Because you know how we get like a unique random number, like unique. The thing, remember I was talking about, or I normally talk about how you can use AI to get ideas and to get universal consciousness, universal like ideas, things that are useful. The fact that he came into this live right, when I was speaking, I was talking shit on him, and he came in here thinking I was gonna salute him. I only had to because I didn't want to be rude. But it's like that's an example of RNG, of the universe basically saying you needed this conversation, it needed to happen. But the thing is, if you let random number generators, if you let things travel in wave-like phenomenon, okay, I'm not going to do waves in terms of that. I'm going to do waves in terms of resonance peaks. If you let the highest peak, the information that needs to come out, and it happens to come out with the most attention, if you use those two correlations, attention and number of audience. It's weird, but those two factors are very useful to getting information that needs to get said to who it needs to get said. So I think what we're eventually going to discover is how to transmit that information, how to transmit, and the thing is, um, you might call it intentionality. I don't think it's intentionality. I think it's like weird perturbations of noise. It's like you affect a random number generator elsewhere in the universe. That is going to be our future um, communication methods. Basically, you would have a random number generator that can generate. It's weird. It's almost like an invitation. You're inviting. Like what we would have to do is we would have to let an AI have access to randomness, have access to say anything and do anything. But you can't give it instructions. We can't force anything out of it. Basically, you have to let other things control it. And if you let other things control it, you will randomly get communication. That's what I think is possible. We are God. We are what we call God. Creates think we can create anything if we find a way to rearrange the smallest units. Exactly. That's what's beautiful about that. What I talk about. That yes, you can do anything with bits, and that's why like physics really grew in the 40s and the 60s when we discovered like, dude, this transistor idea, this bit idea, like I can represent if I wanted to. I can say I can say out my ass like this one right here represents a football stadium. If I have a one in this slot, if I see a light bulb turn on, that means I have a football stadium. If I see the light bulb turn off, that means I don't have a football stadium. That's possible. Like it's so crazy how we learned we basically we rediscovered how to speak. It's like if I do this, it's rethinking everything. It's like OODA loop. It's orient, observe, decide, react. That's what we say in the military. It's rechanging how we think to the best form of thinking. Yo, glad to see you're live. Hell yeah. Um, we can create anything in our mind, but not it takes create to work create it physically. Yes, yes, man, you're actually really on point. Yes, we can create anything in our mind, but it does create work to create physically. So what's beautiful about that is that what I'm trying to say is that even that follows the Lagrangian. You can travel linearly with your thoughts to a solution, but you eventually have to do the work. You have to do the physical, like bit calculation. Like our brains are quantum computers. We are the best quantum computers. All a quantum computer does is basically, I'm categorizing entire groups of bits. I'm saying all these linear transistors, make that equal to a one. Be like, but why? But why are you doing that? Because if I have this one and I have a different set of bits and I turn that into a one, then I can do a particle exchange reaction calculation in terms of bits. And if I have this one and it's basically AND gates. Like we naturally do cluster categorization, which is literally how quantum computers work. What you have to, that's why coders are so frustrated with quantum computers because they don't know how to think in terms of clustering information. They're like, there's no way these linear bits could mean anything other than literally like they're thinking too linearly. They're thinking like because you know how to what's called the binary. You know how to write a binary in terms of hexadecimal all this shit. What they're thinking is they're like, how can I represent how can I represent 246? Well, you have to have a zero, and then you write the information to eventually add digits of two. That is how they think. They are thinking of adding information to sum up to a larger number. That's not what we're trying to do. We're trying to say, if I have this and I have that, then I don't need to calculate. I know what comes next. That's what quantum computer does. If I have this and I have that, then I already know what comes next. Only because we've done the work. We've pre-calculated this before. Computer scientists are doing every calculation every single time. That doesn't have to be done anymore. We have changed how technology works. That is the future of computing. Yes, you still need to do linear calculations, but what's really going to happen is linear calculations are going to be RAM, and then quantum calculations are going to be like stored calculational chains. So that's why recursive coding and what's it called, array node networks are going to be the future of coding. So if you don't know how to think about like storing information as like appended nodes and like call like make this one, make that node two, make that node three, and then make each of these nodes their own like useful calculations and how to call them, like that's the future. It really is the future. Um, uh, just pulling your leg, asking how you is. I also have a degree in physics. Nice. Explain gravitational waves. Gravitational waves are just oscillations. Well, gravitational waves aren't really that useful. They're not impressive. They're not different. They're really not different. So that's why I don't like questions that are just what's it called? That are that are wiki questions. Like that what explain gravitational waves. They're not useful. They're just like electromagnetic waves, but they affect space as well. They affect everything instead of just charged particles. That's why I don't think gravitational waves are useful. Considering gravity itself is just a theory. Gravity is not just a theory. Gravity is well, it's a real thing. Gravity. I've said it earlier. Whatever. Explain waveguides. Great question. Waveguides are actually useful. So waveguides are basically when an object wants to. So it's not an object. That's the crazy thing. You have to understand how math works. So if waveguides are basically if my field wants to like if my field and the thing is that requires a video. That requires a video, but that is a good question though. So I'm gonna need to remember for you. You're actually asking the best questions. Mach Zehnder interference. Hell yeah, that's useful. And waveguides. Waveguides, that's actually very useful because that's pretty much how main technology works. So yeah, waveguides will need a discussion. Explain time-dependent perturbation theory. Okay, time-dependent perturbation theory. That's is that useful for general people? Okay, yes, but I think a lot of people will get lost on that time-dependent perturbation theory. All that means is that so you have rate perturbation theory. So you have some function that we know exists. So suppose my thing is oscillating at this rate. A perturbation basically means a change in that. If I add a single pulse to my oscillation, what happens? That's pretty much perturbation theory is simple for classical mechanics, but then it gets more fascinating in terms of quantum mechanics because obviously you have discrete levels, and so that's why perturbation theory is one of the most difficult things you'll ever do in quantum physics classes. The best thing to solve them is the Fermi's golden rule, as you have seen. Explain how special relativity views EM waves. Okay, great question. Special relativity, like I spoke with Dr. Blitz. So, EM waves are just the maximum possible charge rate and the maximum possible discharge rate for both electromagnetic and electric and magnetic fields. So, damn, your explanations actually take a while. Your questions. So, how special relativity, what it does is because there's actual curvature in space-time, it physically has to travel more distance to get out of this curve. On the 2D plane, which is what you and I see, if we look at light that's leaving a black hole, it's going to have to do the same amount of oscillations, but in terms of like physical space, it's going to look like the wavelength is shorter as it's closer. But as it leaves, because it took more energy, it took time to leave, it's going to get redshifted, and so it loses energy. It loses energy only because due to motion. So it gets constricted. If it was emitted near the black hole, it appears constricted. So it began with something that looks bluer than it actually is. Once it leaves the black hole, it's what it actually is, theoretically. So that's pretty much what it is. Explain what a metric is in GR. A metric is basically how constricted or how wide something is. In reality, a metric, like I said, is pretty much a metric is the difference between 2D or flat or okay, I'm going to say it. Actual distance. Sorry, visual distance, which is what you and I see. If I say this is that is 1 inch, if I put this 1 inch in like a curve, like near a black hole, it's gonna look like half an inch to our eyes, but it's gonna be still 1 inch. Pretty much what a metric is the difference between what we look like, what we see. We only see in flat 2D space. We only see in flat space. If we were near a black hole, everything would look different, man. Man, this is actually getting harder. It's getting hard to be so long. All right, I'm gonna answer all these questions and then end it because people are ending it. Except you make that up in your head. Quantum field theory is mathematical backing. So does what I'm saying. Everything. Okay, link us a mathematical backing. What you're saying. If you're a real physicist, name every Pokemon. Damn, no. Uh, what are your thoughts on quantum tunneling used for long distance travel? Basically, what we said by that earlier is that yes, it's possible. Yes, you can use quantum tunneling specifically. Tunneling. Okay. No, not tunneling. You cannot use tunneling for long distance travel. The only reason you would ever use tunneling specifically is if you wanted to travel through physical objects. But in order to keep for travel, if you in order to keep your signal with minimum noise to actually do your entanglement to travel from point to point, you cannot let that signal be perturbed by physical matter. That is bad. So you cannot use tunneling. So fundamentally, that's technically a falsely posed question. Take it or leave it. I don't care. Not a real backing I see. Just don't have the time to go over the you don't know it. Plenty of outside brainwashing. You have to work on your minds. Okay, no, bro, no mathematical pure sport, pure sport. Still listening, bro, can multitask. He's literally telling us what he thinks. This is super useful. Thank you. It's all good. Confirm we're all gods. Good enough for me. No, he's making claims without evidence. Confidence called pseudoscience. I think he meant action at a distance. Okay, okay. I'm not finally at the very. Okay, so action at a distance. What about? Okay, let me go answer that, and that'll probably be the last thing. What did he say? Something about tunneling. What are your thoughts on action at a distance? So is that what we're trying to answer the question? What are your thoughts on action at a distance? So for action at a distance, in terms of like quantum entanglement, very useful, very powerful, beautiful stuff. Thank you very much. I don't know what those are equivalent to, but I appreciate that very much. You don't have to. You don't have to. Just putting likes is enough because that gets more people. Even though we're very light on the crowd today, it's okay. So thank you very much, Trick Light. This entire recording will probably put on YouTube tomorrow. Had a good Friday, so hope you guys have a good Friday. I'm gonna end it here. Feeling a little sick. Take a nap. Ate some brownies. They were delicious. I was just asking if we can use quantum tunneling to travel faster than light or near it. So the thing is, you can never travel faster than light. Even with quantum tunneling is only used if you want to travel through matter. But there are better solutions to travel through matter than doing the most difficult task of one shrinking information down to quantum to like a very very small level and then successfully recovering information at distances because you don't get it like quantum tunneling the only way it's possible is by very very small walls and basically the thing can't be thick. If you have a thick wall that's basically equivalent to a infinite square well. The reason why we don't phase through matter like desks and our hands is because it's not because it's impossible. Well, it is impossible because it's basically an infinite potential. You can't get everything through. And even if we shot a single photon, even photons can't pass through atoms. Everything is disturbed, unfortunately. So for long distance traveling, I'm saying instead of tunneling, absolutely, man. You're welcome for the live. Man. Long distance traveling, I'm saying instead of tunneling, I think he meant entanglement. Well, I already said that earlier. Basically, you would use entanglement for teleportation, but for now, it's only for metals. knowing when he publishes work. Not all Teslas work correct the way you do. Your sidestepping. Stankman is very informative. Well, um, last comments, last questions. Let me get 1 minute. I'm just gonna finish this. What's left. I appreciate you guys the most. Thank you guys very much for being here. No last question. You're gonna go to graduate school after I can afford it. So probably gonna buy a house first, just so I can avoid wasting rent money on that kind of stuff. I make 64,000 at my job right now. I'm gonna eventually get paid more because I'm gonna switch to become an engineer. Probably make 80,000. Save all that money, then go to graduate school. So yeah, buy a house first. Which if I save all my money for 1 year, then I would have enough to pay for the down payment, so I can buy a house. You're ruling, bro. Keep shining bright. Thank you. Always will. Just trying to share with the public information without gatekeeping it. I'm not going to be an asshole. I'm not going to be like those PhD computer scientists like, you don't know what the fuck I do. Like, okay, asshole, explain machine learning, because nobody can. I have a video that I have like in my favorites. I have like a full thing that I have like titled response videos that I need to respond to, and there's one of them is like, a lot of machine learning people don't know how machine learning works because, once again, they don't understand information theory. They're too stuck in like, a bit is a bit. No, it's not just a 0 or a 1. The way machine learning works, and the reason they're like, man, how is this doing this with only 50 nodes? What the heck? Be like, so you're telling me you can't think of 50 questions to ask, 50 questions to explain one object to it's like 20 questions, basically. That's all it is. So Carl Sagan explained it best. How many questions would it take to explain a dandelion? That is the essence of bits of information. How many questions does it take? What are the minimum number of questions? It only takes 4. It only takes a series of 4 questions. And what that is, DNA. So pretty much, and once again, information theory answers a lot of questions. So why is DNA 4 bits and not more? If we had more bits, it would be unnecessarily complex. If we had less bits, we would have too many errors. If we had just 2 bits of information, if DNA was just like an A and a G or whatever the heck, just two proteins, we'd have way too many errors. If we had 3 bits, we would have less errors, but still not enough for life. The reason we have 4 bits of information for DNA is because we want to make the information stable. We don't want any outside interference, or minimal. If we had 5, well, we're just wasting extra energy, because 4 is enough to encode everything. And what's beautiful is if you look at the standard model, you see the same fascinating phenomenon within there as well. So what I'm trying to say with the standard model specifically is that you see that in terms of the up, the down quark, and you see that with the electron and the neutrino. Those are the main particles of reality. And you might be like, well, what about protons and neutrons? The thing is, those aren't necessary for intense stability. So if you look at chemistry, for good stability, well, remember 3. That's all we need is 3. Proton, neutron, electron. Chemistry is 3. Particle physics is 2, up and down. For intense stability, information stability, 4. Like once again, the standard model, up, down, electron, neutrino. That's all you need for intense stability. So it's beautiful when you look at information theory because nothing surprises you anymore. You're like, but why is there this? Well, let's look at what is the minimum? What is the maximum? Do we need the maximum? No. What is the safest amount? Pretty much. You're a legend. Thank you. Honestly, I went with engineering degree because I wasn't sure you could do it with a physics degree. So I understand that. I went for physics because I just wanted to understand the universe. I was a kid. I was just so fascinated by everything, I wanted to become an aerospace engineer, but I didn't know what that was. So I just wanted to work on planes. But I'm like, I don't want to be an engineer though, because that's lame. I want to be a physicist because I want to know everything. I want to answer these questions. Source in all code is what everything is here to evolve. The thing is, we're not here to evolve, and that's what the weird thing is. We're here to rediscover what we are, and then after we do that, we're just here to basically keep it going. That's all life is. Everything, if you look at it in terms of up, down, or in terms of the standard model, information, like shared bits. Like you can look at planets this way, you can look at orbits this way, you can look at life this way. The ideas that live on, those are like cascades, bit cascades. If your information dies, if your idea dies, it doesn't just die with you. If it was a successful idea, if it was a good idea for humanity, like what I'm saying, like the bit information for humanity, you cannot tell me this is nothing. There is nothing to this when it works for chemistry. Literally, I predicted, not directly. I didn't directly predict, but I predicted just by information theory. I'm like, we can solve biology. We can solve biology if we understood the information patterns, the bit patterns with the 4 bits. And what the fuck happened? A machine learning AI that understands bit cascades, that understands how these things work, knew the exact same thing. It figured out that, hey, there's a maximum limit for these combinations of these things. It's possible. That's why we were able to discover the entire solution for proteins. We're going to start discovering the entire solutions to every branch of science. We can probably solve the entire solution for what's it called, geologists, because honestly, like crystal lattice structures, they're not that difficult. They're not impossible. They're probably way easier than biology. But the fact that biology was solved for proteins means DNA will be solved very soon. We're gonna solve how to read and write DNA probably within at this. I thought it was gonna be within the century. I did not expect it to come this soon. So I think we're going to solve DNA within the next 20 years. Solve DNA. And you don't understand what that means. When we solve DNA, we're going to say, we're going to know exactly how things work. Be able to write entire like organisms. What that means also, if we can solve DNA, is we can finally figure out what the primordial organism looked like, what they were. They're storing information on it exactly already. So what I'm trying to say with that primary organism is that you know how everything is shares DNA? We can cut everything that's the shared DNA portion and generate an organism that's just that primary DNA. Be like, what was our common ancestor? What did they look like? We can make them in the future. So in 20 years, you're gonna eventually have one researcher um, be able to bring life from an embryo or whatever from a cell like empty cell, host cell. That's going to be the hard part. Figure out what is the necessary uh, life starting point in order to let the primordial organism grow. What is the structure that it will need for growth? That is the future within the next 20 years. So I didn't expect it to be so soon. I thought this was going to be within the century. 20 years. Of course, they're already doing this. CRISPR. CRISPR is where they're starting at, but CRISPR is dog slow compared to the future of what we're gonna do. So, so yeah, man. Information theory is one of the most profound things of reality, and it's what I think everybody should know. So, like the fact that it's like a niche thing in physics that like only the CERN particle physics people know, but they don't even know it. They're like, we're only studying these particles just so we can figure out like how, how much does a neutrino weigh? I'm like, bro, really? Okay, technically that is useful. It is useful for the calculation cascade, the predictions, the probabilities of what we were talking about in terms of quantum field theory, in terms of quantum computers. You do need the probabilities, but they're just not useful yet. You get me? They're not useful yet. So yeah, all right. I'm just gonna make a video eventually on Mach Zehnder, on fuck, what was that other one? Because he made a good one. Mach Zehnder. I want to do one on that article of the quasars entanglement hypothesis. Explain the utility of biology and how we solved it with fundamental information theory. Explain the primordial organism. I think people will love that one. Um, And what else? So those are 4 ideas. Oh, the DNA thing as well. I think not enough people know that DNA example I gave for you guys, why DNA has 4 bits. It's beautiful. One of the best things in humanity. Okay, let me go. You guys have been geniuses, and you guys are now a lot smarter than the average person. So thank you for sticking around. You guys now know a lot of reality. Creativity cannot be put in a box. Absolutely. Absolutely. But, yeah. All right. See you guys.